Welcome. In this lesson, we are going to answer the question, does the derivative always exist? So recall from our lesson on derivatives that f prime at x, the derivative, is equal to this limit. But we put this condition, we said if this limit exists. So the question is, what happens if it doesn't exist? And the simple answer to that is, if this limit does not exist, then the derivative will not exist. So if the limit doesn't exist, does not exist, and now usually it won't exist just at a specific point, at a specific x value. So it might exist at certain x values on a function, but not at others. At x equals a, then the derivative won't exist, but just at that point. So it's possible that the derivative exists at some point for functions, but not at others. Does not exist. And in that case, we have a special name for that. So we say f at x is non-differentiable. So differentiable just means, can you take the derivative? So you can't take the derivative if the limit does not exist. If it were differentiable, if this limit does exist, then we say it is differentiable. So that gives us the answer to this question. So the easy answer is no. The derivative does not always exist. But really, let's the useful thing here would be to look at examples to see when that happens. So let's use f at x equals absolute x differentiable at, and we're just going to look at a specific point, x equals 0. So let's graph it to see what might be a problem here. So absolute x looks something like that, except that line should be straighter. So if you don't remember absolutes, maybe take a look back at the absolutes video. So we're asking about this point, x equals 0. So we want to know, is it differentiable there? And just looking, let me sort of zoom in to what's happening just kind of in this area here. What we have there is, it's kind of like a corner, two straight lines meeting. We want to figure out what the slope of the tangent is at this point. But if you remember what a tangent means, it's sort of approximation of the function, or really close. But really close, it's still a corner. So how do I draw a line that approximates a corner? Do I draw it like that? Do I draw it so it sort of matches one side of the corner or the other side of the corner? I don't know. So I'm not sure how to draw the tangent there. So let's use that definition of derivative at 0. So f at 0 plus h to see what sort of the problem might be here. So this is our definition. Limit as h goes to 0, so don't forget that. So limit as h goes to 0 of f at 0 plus h. So f in this case is this. So that would be 0 plus h absolute minus absolute 0 over h. Limit h goes to 0 of, this would be absolute of h minus 0 over h. So we've got limits h goes to 0 of absolute value of h all over h. Okay, now how do we evaluate this limit? You can't use direct substitution, 0 over 0. And then you can't reduce because it's a, you can't cancel anything out because this is absolute and this is not. So if you remember how we dealt with limits with absolutes, we had to treat it as a piecewise function. So remember that absolute h is really just equal to h if h is bigger than or equal to 0, and negative h if h is less than 0. So we're going to take a left limit from the left of absolute h over h, and we're going to take a right limit plus. So plus of absolute h over h. So let's look at this left limit. So this is 0 from the left. So limit as h goes at 0 from the left. So from the left, so 0, numbers smaller than 0 but close to 0. Smaller than 0 would mean I'm on this piece, so it's going to be negative h over h. H is go, so it's a limit as h goes to 0 from the left of minus 1 over 1. And if you let h go to 0, this would just equal negative 1. And the same thing for the right limit. But for the right limit, you're taking h values bigger than 0. So like, small, close to 0, but bigger. So that would be this piece. Right? It's bigger than 0. So it would just be h over h, which would be the limit as h goes to 0 of, and that would cancel out, and you would just get 1. So this would be equal to 1. So notice the limits, so not equal. And if our left and right limits are not equal, then you can say the overall limit does not exist. So therefore the limit, that original limit that we were doing, f at 0 plus h minus f at 0 over h, does not exist, because the left and right limits are not equal. So therefore f at x is non-differentiable at x equals 0. Okay. So just to look back at that graph, so what we got for our left limit was negative 1, which makes sense because that's the slope of this line, and what we got for our right limit was 1, so which makes sense because that's the slope of this piece, right? So, but there was no sort of consensus on the derivative at the middle, so it would be said to be non-differentiable. So let's look at another example. Another way a function can be non-differentiable. So same question, why is this function differentiable at, write that down, at, we'll use the same point, x equals 0. So what is this function? You might recognize this as the inverse of this. So, if you want to graph this, it might help to graph this one first. So x to the third, most people, you would have seen this. That's x to the third. Then how do you graph an inverse? You reflect it in the y equals x line. So a reflection of x to the third in the y equals x line would look like, sort of like that. And we're looking for the derivative at this point. So let's do the formula, and then we'll see sort of why that might not be differentiable, or it turns out it's not. So this is f prime at 0. All over h, limit, so f at 0 plus h would be 0 plus h, and then f was x to the 1/3 minus 0 to the 1/3 all over h, which sort of works down to h to the 1/3 all over h, which is the limit as h goes to 0 of, so we have h to the 1/3 over h to the 1. When you're dividing, you subtract exponents, so that would be 1 over h to the 2/3. So what's happening here is h is getting very small. So this thing, the denominator of this fraction or rational expression, is going to 0. So we have 1 over a very, very small number. A 1 over a very small number is a very large number. So this thing is actually approaching infinity. So what that means, and you can maybe see this in the graph, is that the slope at 0 is going to infinity, meaning it's a infinite slope. You could think of as a vertical tangent, but technically, an infinite slope, you can't write an infinite slope. There's no way to write that. So the derivative doesn't exist here because we have a vertical tangent. So it's sort of, the tangent would be kind of straight up and down. That's not quite vertical the way I drew it, but hopefully you can see it. Okay, so that's two common ways. Let me go down. Two common ways a derivative won't exist. And I'm going to summarize it actually with 3 common ways. So the 2 that we looked at, and then I'll add one. I won't do an example of it, but you should be able to see why it wouldn't exist, and maybe you'll do some exercises where that happens. So derivative does not exist. So the first way was just our first example, where we had a corner. So this came up with an absolute, and that's probably the most common way you're going to see that. A corner. So we saw that sort of the slope was one thing on one side, but one thing on the other. So the derivative didn't exist. Sort of a similar case, and I'll consider that the same sort of type, is where you get not 2 straight lines meeting at a corner, but 2 curved lines meeting at a corner. So something like that. So, I mean, it's kind of a corner, but, if it's curved lines, we give it a special name. We call it a cusp. So that can come up. And that one actually won't just be absolutes. You'll see it comes up in different cases. But the same problem. Your left limit and right limit do not match up. And then the second one was a vertical tangent. So we saw that was something like that. So right at that point where you had the tangent would be sort of vertical. So, and it makes sense that the derivative doesn't exist there because you can't have the slope of a vertical line, right? What would it be? Infinity, but that's not really a number. We can't really write that. So you can't get a vertical tangent. And the third one is a discontinuity. Okay, so we sort of saw a bunch of different types of discontinuities, right? You had the point discontinuity, right? So the derivative wouldn't exist if there's a point discontinuity. We saw a infinite discontinuity, so an asymptote, so something like that. This was a. So there wouldn't be a derivative there. So derivative doesn't exist when you have an asymptote. Or the other one was a jump discontinuity. So there, you wouldn't have, the derivative would not exist, right? And sort of the easy way to see it is that you can't draw a tangent, right? You can't approximate the curve where the curve does not exist, or the curve's different things at near a point. So those are your 3 common types: the corner, the vertical tangent, and the discontinuity. And you can prove them all that they don't exist just by using that definition of derivative.